Hello guys, today I'll be explaining the project on the common emitter amplifier. So let us start. As you can see, your aim is to design and gain of a bipolar transistor amplifier. In this case, it's a common emitter amplifier, we call it. Then, as you can see, the outcome is here. What is required of you is that you have to calculate the values or design the values for R1, R2, RC and RE. Then you do the simulation for the this circuit. So you have to do the DC biasing and the DC and the AC analysis of the uh, common emitter amplifier. Then you build the uh, circuit connection on the breadboard, and then you build it in practical as with a experiment. Then you use a function generator and oscilloscope to do your measurement and everything. Yeah. Then you can go through the project criteria. Then here the components which you are given. Number one is the transistors you are given. There are three transistors you can use. I know you are given two of them, the 2N221 and the BC547. So this is how 2N22 looks like. It's a silver transistor, as you can see. Then if you write on Google the pin out for 2N227, then it will show you the pin out is. Then it's the same thing for BC547. Let me write BC547 transistor. So it's a black transistor, as you can see, and then it's written on it BC547, as you can see there. And then you can also write pin outage, then it will show you the pin outage like here. It's given, then you have a flat face and the other side is round. So these are the two transistors you can use. Um, and then also you have to check their data sheet, I would recommend, because both of them are different values. So if you decide to use BC547, I think so its beta is around 300, and if you use 2N22, its beta is 200, the beta value. So you have to check the data sheet which one you are using, this one or this one, then according to that your beta value be different. Then we go to point 2 where it says the capacitor. There are two capacitors there, these two, and you can choose between 1 microfarad and 10 microfarad. So those two capacitors are this one. This is we call it the input capacitor. Here we call it the output capacitor. Here you have your out, V out, and here you have your V in. So this is the input capacitor, output capacitor. You can have 10 microfarads there and also 10 microfarads here, or 1 microfarad, any capacitor between these two values. You can put it there. And it's a good idea if the C1 and C2 are the same value. It just works better. Then number 3 says one capacitor 100 microfarads. So 100 microfarads it's CE, this capacitor here, and we also call it the bypass capacitor. Just remember that. And just remember the function of bypass capacitor is to increase the gain of the system, because when you do your AC analysis or the small signal analysis, due to this bypass capacitor the gain increases. If you remove this bypass capacitor, you will see the gain of the system will be reduced or much smaller compared to when you connect the bypass capacitor. And then you have your resistor here. They say do your calculation and they say your load resistor is 10k. So this is your RL here, which will be 10 kilo ohms or 10k I'll say. So that's your RL, 10 kilo ohms. That's your RL. Now that's your lab work whenever you supply, as you can see. They say you use a function generator amplitude. So they will show you this will be your function generator FG from 100 millivolts peak to peak to 110 millivolts to peak to 100 volts peak to peak. I would recommend use 100 millivolts peak to peak. That's better. Uh, it gives you a better graph compared to use this 10 millivolts. Then gives you issue. So use 100 millivolts peak to peak. Gives you a better view. And when you do the system again, then it gives you or when you do the simulation, then it gives you a better view. And when you compare it to do when you do it, when you build it and you do the experiment, and you supply again 100 millivolts peak to peak. So it gives you a better view of how the system looks. And this 15 DC volts, it's your voltage here, your VCC. That's 15. Then as I said, your 100 to 100 millivolts, it's this VS, 100 millivolts. That's your 15 millivolts, 100 millivolts. So that's 1, 5, and then that's 100 millivolts. That's your VS. Just remember that. So this is your sine wave and this is just the DC voltage. Then as you can see here, they said the preparation for experiment 3, design a single stage bypass common emitter design. So that's single. So this is just remember single stage amplifier with a bypass capacitor. That's why they put a bypass there. Your supply voltage, as I said, 15 volts DC. Your meter current is the last two digits of your student number. So the example is given here, as you can see. Example is given. So if your student number ends with 3.2, in this case it ends with 3.2, then your current will be 3.2. Or let's say your student ends with or let's say if your student number is something like this, I'll say 22679, something like that, right? Then your current will be the last two numbers, which will be 8.9 milliamps. So that will be your current. Or let's say again, we change it to 2122 or something like this. Then your current will be 1.0 milliamps. So it's for just 1 milliamps. Or maybe it's 0.9. So your current will be 0.9 milliamps or something like that. Or maybe so that will be your current. So that will be your current. Your collector your emitter current or your collector current that you will use to do your calculation. And I hope you know how to do your DC biasing calculations, where they say your VRC and your VCE is same, which is 45% of the VCC, as you can see here. So to calculate your what do you call your RE, you know your VB is 0.7, and they say your VE is 10% of the VCC. So 10% of VCC is 1.5. Then you divide that by your emitter current, that will give you RE. Then you can do the same here. So you will find your VRC using that value, of 45% of the what do you call VCC and everything. So I hope you do know how to do the calculations and those things. Your DC biasing calculations and your small signal analysis. That's where you will see your gain and everything. And then here are the instructions you have to follow. I would recommend you read through them step by step and see what they ask, because you will do the same thing when you build a simulation. You will answer the same questions, and as it is asked here. So you do the simulation, you see they ask for VBVE, then you write that down into table 1 here. And then when you are done with your simulation, part 2 says you do the AC part of that, where you supply a signal of, as they said, 10 millivolts peak to peak. I'd recommend you use 100. That gives you a better view. I use 100 millivolts peak to peak. That gives you a better view. So we are here. So let's design system. So first we need to calculate R1, R2, RC, and RE. So I'll use this number here. Let's say this number it ends with 3.2 milliamps. Let's say this is the student number I'm using, so it's 3.2 milliamps. So I'll use this as my emitter current or your collector current, more or less. And then my VCC will be 15, and then I'll use 2N22. So its beta value is 200. It's more or less 200, somewhere there. So what will I do? Let's do some calculation. I wrote a program here which can do the calculation for me. So I'll put in my DC voltage is 15, my beta is 200, my current was 3.2. It was 3.2 milliamps. Yeah, 3.2 milliamps. 3.2. Then as you can see, my system does give me a good values here. So my RC is 2.2 kilo ohms, my RE 470, my R1 is 39 kilo ohms, and my R2 is 6.8 kilo ohms. So I'll use those two values. So let's start. And I hope you did check the video on LTspice, how to use and everything. So first we'll start with building the circuit, and first thing we'll do is DC biasing of the circuit. So let's build. So I'll get the resistor here. You can get a resistor by pressing a letter R on your keyboard, or you just select and drag it here. So R, I need 1, 2, 3, and 4. So I'll rename this to, and then to rename is you can hover over the name, then right click. You can rename that to RC. Again, you hover over it, you click RE, then you hover over it, you right click, press, you can change the name. Then as you can see this AND gate here, it shows me it's my component. I go there. Then here I'm using an NPN transistor. I press OK. I put there my NPN transistor. Now to change this value, I will do this. You hover over your transistor, then you right click. When you see this arrowhead here, you see when you see the arrowhead or the hand you're pointing, then you press, then you say pick a transistor there. Then you can do two. Then here you have all the transistors you want. In simulation, most of the time they only have 2 and 2, 2, the first one. And then if you go to the side, as you can see, the beta is what? 200. So I'll select that. So I'm using 2 and 2, 2. That's my transistor. Then I need a voltage source here. I will get a voltage. That's my DC voltage or my VCC. I'll rename it. You go to the name, hover over it, you right click, then you rename it to VCC. Then you can also change the value here. Right click on the resistor, on the, what do you call it? The voltage source there. You change it to 15 volts. That's how, so that's our what you call D, VCC. Yeah, that's our VCC there. Now we need also a ground. We can have a ground here. That's better. So at least we know our system is there. Then we use a small hand just to drag it down a bit. Below the same level, make it better. It's better. Yeah, it's much better. Then I'll just connect these two. My positive VCC goes there. Then I connect this there. My transistor will be, let's say it will be connected, and these two are connected. Then I have a differential here, so that's how it's connected. I press escape. Then to let's say to make it in the view, let's say I'll show you something. Then my negative goes to ground there. So let's say I have zoomed in too much. You can press escape. Then I want to see my whole circuit. You just press the space bar on your keyboard, then it adjusts it. It adjusts the this like this, so you can watch. You can see the whole thing. Then as you can see, I need to put in my value. My RC is 2.2K. So I'll put. You can put 2000. I'll put 2200. My RE is 470. Right click. Then I select that. This one was I think so 39,000, and this one was 6,800. So I think so this is our DC biasing part of the system. So this is how we are going to do DC biasing. First thing you will do, you will be label. So we'll have VB, we'll have VB here. Let's go to the document. As you can see, they want VCC, VB, VE, VBE, IE, VC, VCE, and RC. So you will have your VB here, then this here you will have your VE, here you will have your VC, your collector of voltage or things like that. That's your VC, so your voltage across the, or not VC, more like we can say this voltage here is the combination of from uh, uh, this, it adds up all the VE and your VCE. So that voltage will add that, so that will be your added voltage there. So you can say that's more like VCE. You will measure the voltage here, it's VCE more like your collector voltage plus your emitter voltage. Then your VCC will be 15. Your VBE is, it's 0.7 in simulation. So it's a voltage across here. There's a voltage drop which is always 0.7. In your simulation, it will be the same 0.7. So you can leave that. So your VC, you will just minus, or your VRC. You will find your VR, so that's your VC. So you'll find your VRC over when you minus 15 minus VC. Then you will find your VRC. So that's around, this is VC. Then your VCE, VC and VCE will, VRC will be the same value more or less, and your emitter current will be also given. So that will be our VB. Let me rename it to be VB. Then my again another one I'll need VC. So my VC will be here, then VE will be here. Call that VE. Then I'll label another one VCC. Then this will be here. That's the VCC voltage. So you will minus VC, VCC minus VC, that will give you VRC. Then when you minus, there's a voltage drop here, VCE. So how you can do that is, you can minus VC minus VE. That will give you a voltage drop across there. Yeah. Then this is our circuit for this. For the, what do you call, for DC biasing, it's ready. So how are we going to do the DC biasing? So for DC biasing, it's quite simple. You just go to simulate run, and I think so. When we do a simple DC operating point, you press that. That's DC operating point. Gives you the values. So as you can see, VCC is that, and as you can see, our VB is 2.14. That's good. VC 8 point. Yeah, I agree with that. Then as you can see, our simulation value is not exact, but it does give us that our voltage is more or less 1.5 volts across VRE. Then if we check our emitter voltage or the current, As you can see, it's 3.1, which is, I think so it's good, which is close to 3.2 milliamp. So in some of your simulations also, your collector current will change because we are not using the exact value, we are using the closest E12 value. So yeah, then we can see our voltage across IRC is same as the collector current. Voltage across RE is same as the emitter current. So this is, you'll use this table here to fill in table 1 and everything. That is 0.7. Then let's see if we can get a voltage here. I'll name it VBE. Let's see how much voltage do we get at this point. Then again you just run. Yeah, VBE. Where's it? Oh, it's not it. Yeah, but then we get our values. Now we do the AC part of the circuit where we add the function generator and everything, right? Now to do the AC part, we'll have our, what do you call, we'll have our, what, uh, a capacitor, the load and the signal coming here. So now we'll connect this part of the circuit here. And this part of the circuit and this part of the circuit. Let me erase that. So I'll be connecting in the IE, CE, VCC, C2, C1, C2, RL, and RS. So for RS, you can make it a small value such that your gain is bigger. Let's say you can use how many? Let's make it for RS you can use 680 ohms. That should be a good enough value. So because I think in this document RS wasn't given, so we'll use RS as 680 ohms. And then our C1, C2 will be 10 microfarads. Then our CE will be 100 microfarads. RL is given, which is 10K. Then our signal will be, what did they say here? They should specify. We'll use 1 kilohertz. Our signal will be 1 kilohertz, and let's make that this we can change it to 100 millivolts peak to peak. So Vs is 1 kilohertz and 100 millivolts peak to peak. So let's do that in LTspice now. First thing we need is a capacitor. Then I can press Ctrl R to rotate that. Then I need one there, and I need one here. Now let me do this. Disconnect that. I'll connect it later. Uh, then I need my RL here. and then my RS here. So I'll call this one CE. I'll call this one C1. I'll call this one C2. This is for microfarad. You can just put 10U. That gives you the micro. And even here 10U. You can put also F. It works the same. Capital letter F. And even for this one, it's 100 microfarads. And then let's just move this far away and you can see. Yeah. Now we go to components here. Now we need a signal generator. So you just write signal, and as you can see, we get a signal here. You select that, you press OK. So this is our signal generator. Then as you can see, if you right click on the signal generator here, you go there, you right click, you see it's DC offset, we don't have offset. Then the amplitude of the signal generator and the frequency. So our peak to peak is what? 100, right? So millivolts. So our amplitude will be 50 millivolts. As you can see here, we have a box for small signal analysis AC if you want to use it, but mostly it's better to use this one. And just remember, it's a sine wave. You press OK. So that's 15 millivolts. That will give us 100 millivolts peak to peak. So now let's connect that. And just remember, all the grounds in this circuit are the same. There is no different ground. Then my load resistor will connect there. Then I'll just check this one like so. So it's easier to see where is what connected. And then I'll change this resistor here to 10. You can also put K there, so it just shows you it's a 10 kilo ohm. Then I'll rename it to RL, so it's a loader resistor RS. And then this I said it was 680. That's a good value. Yeah. So this is our resistor now, right? This is our whole emitter amplifier. As you can see, there is no offset. We have the amplitude of 50 millivolts, 1 kilohertz frequency. Then we have our values here. Our DC input is 15 volts, as you can see there. So to simulate this, you go to run. Now here you will select transient. Transient is just a constant time. Then you can make a stop time of, let's say, 1 second or something like that. Time to start saving the data, you can put that there. I'll start from 0. Maximum times steps, you can put that also. Then you press OK. Then when you press OK, everything is given here. You have the two system here, right? You got your oscilloscope here. Then you have your circuit here. Then if you hover towards it, as you can see, if I can zoom in, as you can see when you hover towards it, this symbol here, as you can see, it shows it's a current. So it's used to measure current. This probe, when it shows something like this, a probe, it's a voltage. Remember that. So in this case, we'll be measuring the input voltage. As you can see, that's our signal, which is 1 second is, I think so, too big. Let's change the value there. such that we have at least a better view of the signal. So I'll right click on there. I'll make my time to be 100 milliseconds. That should give us a better. Now again I use my probe. Yeah, you see that's our input side wave, the green. And as you can see 50 millivolts amplitude minus 50. So peak to peak is how much? 100. Then that's my output here at this point. When I put that, you see my blue wave is my output. Then if I select my blue or my white, you can have two windows here. In this case I have one, but as you can see it's an amplifier, it's working, right? So if I select my blue view, then I can move this cursor here. Then I see my peak to peak voltage here on the bottom on draft, or I can do the same for my smaller. I just move it on my wave at the bottom. As you can see what frequency at time, and then that's our voltage. So these are the values, and this is the waveform you will draw here on number 2. So this is the waveform you will draw. Then you will write the reason which our peak or the negative starts distorting. I'll come back to this, but this is what you will do. So for this part here you will draw that sine wave, and then if we zoom in, let's say press escape, and if we zoom in, as you can see the amplifier is working quite well. Right click, zoom to fit. Then I just want to show you something. As you can see, this wave is inverting, so the system is working all right. So how can I show? Let zoom fit, so it's working all right. So your output should look something like this. Let's say this is your input waveform, right? Then your output waveform should something like this. It should be amplified, but in the different direction. The blue one is your input waveform, the green one is your output waveform, but it's bigger and amplified. That's how it should look like. So that's what it is. Now they say, which output peak distorts first when the input amplitude is reached. So what do they mean by this part here, distort? A distortion they mean by is when you change the input value. Let's say I increase my input value to 500 millivolts and I press OK. Then I check again. Let me just run the simulation. It runs again my input waveform, as you can see, and that's my output waveform. And then as you can see, my waveforms is getting much more flatter or squarer, right? So that's what they mean by that. So you have to look for the exact value. At what value does it start giving getting flatter out, and which peak. So in this case I think so my positive peak is starting to distort, because it's a bigger difference compared to my negative peak. So for me it's a positive peak which is getting distorted because it's getting flatter. Much it has more flat. So you check it by increasing your input value. Then again I change that. Then I can increase it to, let's say, 200. You press OK, then you press run. Then it gives you the value. And then as you can see in this case, my positive peak is getting distorted first. Then zoom to fit. as you can see. So yeah, the therefore for me it's a positive P. So first you have to check and then you must reason why does it distort. Then you draw the waveform as seen on the oscilloscope. So you draw this waveform, the distorted waveform here. You draw the distorted waveform here. Just remember that. That's the normal waveform. This one is the distorted. It's for this one here. Yeah. And then now we come to number 5, where they say you draw a waveform without a bypass capacitor. So what you do is now you remove your bypass capacitor. So what you do is you take your snipping tool or your scissor. Let just then let's close this. No, consider. Let's stop the simulation. Then let's get the scissors. I cut the bypass capacitor. Alright. Now I remove the bypass capacitor and then this I connect it again. So they said now here you remove the bypass capacitor number 5. Then you run it. When you run again, then you have your probe, your input waveform, and your output waveform. Now, as you can see, your input waveform is not that much, your output is not that much amplified when you remove the bypass capacitor, right? So this is the result they want at number 5. Now you disconnect the emitter, bypass capacitor, or voltage gain with emitter, bypass capacitor. No, this one you can remove. This one should. This graph should be without. I'll recommend you will do a without bypass capacitor. Then you write with bypass capacitor. So your overall gain, just remember your formula should be V out divided by V in. So how will you get these values from simulation? As I showed you, select your graph there. Then you take this value to the peak, right on the peak. Then whatever value you get this. So this is your output value. Your output value. Then you go to your input divided by your peak input value. There. So output divided by your input. Then you get your gain. So that's how we will do that in simulation. Yeah. Yeah, that's all. Then you do this exactly the same process for the practical part. First you do the DC biasing, then the AC analysis, then the AC measurement of the system. Uh, yeah, then you compile all the results I want in the document and you submit. I think so. That's all, guys. Hope you understand this, and if any question you can ask, or yeah, that's all. Thanks.